So a differential equation is an equation that includes a derivative, and I sometimes even think of them as derivative equations because really you're saying a derivative equals. But it's called the differential equations because it could be a second derivative equals. And an ordinary differential equation is an equation involving an independent variable x and a dependent variable y, and the derivatives of y with respect to x. So any differential equations has derivatives built into it. It doesn't have to be dy dx equals by itself. Like this one in A, we could rearrange to get y prime by itself. This second one has the dy dx there. The third one has a double derivative and a first derivative built into it. So anytime you have derivatives in an equation, that makes it a differential equation. The highest order derivative determines the order of a differential equation. So this first one here would be a first order differential equation because we just have a y prime. Same thing with the second one. We just have dy dx. That's a first order differential equation. But in part C, where we have y double prime, that would make it a second order differential equation. So you're just looking for the highest order derivative that appears. This one has a third derivative. Notation-wise, careful in part E. The dy dx, which is a first order derivative, is cubed. This d2y over dx squared, that's a second order derivative. So this one would have an order of 2. The exponent of the highest order derivative in a differential equation is called the degree. I don't know if you remember learning about degrees of functions way back in grade 9. You just looked at the highest exponents of the variable. Now in a differential equation, we're looking at the highest exponents of the highest derivative. So this first one has an order of 1 and also a degree of 1. Second one had an order of 1, and what's the exponent of that derivative? Also a degree of 1. In fact, these first ones are kind of boring. Degree of 1, degree of 1. If the dy dx was the highest order, we would say this has a degree of 3. But since the highest order is the second derivative here, and it has an exponent of 1, it has a degree of 1. Third one has an order of 1, but it would have a degree of 2. So try these 4. I'll put the answers up in a second. And don't look until you're done. So when organizing these, I would look for the order first. What is the highest order of derivative? And once you found that, find out how many times that appears. Or check the exponent on that one. So like in B, the d cubed y over dx cubed, that's order of 3, and it has an exponent of 2, making it a degree of 2. So we use integrals, if it makes sense, to work backwards, right? So if you have a differential equation and you wanted to find the actual equation, you would have to work backwards. So a function is a particular solution to a differential equation. So sometimes they're like, verify that 3x cubed minus 2x plus 5 is a solution to this. So basically, what have they done here? They've given us the second derivative. If you work backwards from a second derivative, does it make sense that going back once you'd have a plus c? And going back twice, you would have a plus c and then a plus c2 or a plus d. And there's a lot of possible solutions. So when we have a differential equation, this is one of the things that is difficult in real life working backwards, is there's a lot of possible solutions that could be above. And unless we have extra data, we don't know what those solutions could be. So this is saying, if you started with this, is this a possibility? Well, if I started with that, could I find its derivative? Yes. dy dx would just be 9x squared minus 2. Could I find the second derivative of that? Yes. The second derivative would be 18x. Does that match up with the equation? If I plug in 18x for the d2y dx squared, does it work? Yes. I mean, you might even, right? You might even rearrange that one and go, oh, they're the same. So if you had a particular solution and you wanted to verify it works, it's much easier to do the derivative of that and see what it looks like, rather than integrate with the plus c and then the plus d and wonder, is this a possibility? By the way, how many things would work for this? Can you see that the 3x cubed was super important, because once you start doing the derivative, that's the only thing that makes the 18x. I could have asked this same question by having a plus 5x minus 135. Because once I do two derivatives of that, can you see that's going to go away? I couldn't have an x squared, because then that eventually would still have a plus number here, and it wouldn't match up. But there's lots of particular solutions. You could have anything here and anything, any constant, anything in front of the x, and it would still work out. So try this one. Practice your derivatives. So not too bad for verifying a solution. Finding a solution can be a little bit more tricky, but not bad. We've actually done this before as well, right? This is just, you've got your derivative. Can you work backwards to find your actual equation? And if you're given a particular solution, you know that at 0, y of 0 is equal to 4. Well, that can help you solve for C. All right, so just a review of that. We know that we could find our function y by integrating and working backwards. No advanced techniques here. Are you still able to do the easy integrals? Right? What's the integral of e to the 2x? It's going to be e to the 2x divided by 2. What do we do with exponents? Add 1 to the exponent and divide. And then we write a plus c. Now we know when x is 0, y is 4, so I can plug in 0 and plug in 4 for y. Do a little bit of algebra and arithmetic and come up with c is 7 over 2. So then our particular solution is the integral with the 7 over 2. So the real life application of this is you're measuring something and you can measure how fast it's changing. So you can make an equation with the rates of change. But you're kind of curious if you can create a model that represents what's changing. Well, then you would have to work backwards and get your original equation. Sounds nice and easy. We're going to find out in real life sometimes when we get these equations of things that are changing, integrals don't always work out nicely for us. We've already learned a whole bunch of advanced techniques. But you're right on the line of getting an equation where you can't actually do the integral of. It's not possible. So now we're going to look at, well, how can we still do those things if we can't find those equations? But that's coming up. A curve has a slope of 8 cos 4x at each point on the curve. What is the equation of this curve if it passes through the point pi over 8, comma, negative 2? A slope of a tangent is the derivative. So we know that dy dx is 8 cos 4x.
Oh, sorry.
All right. Test your integral skills. I'll put that answer up in a second. Integral of cos is sine, but that 4x means that you would have to divide by 4, so I did the 8 divided by 4 and got 2. There's my indefinite integral to plus c, because I have an initial condition. I know that pi over 8, it's equal to negative 2, so I can plug in pi over 8, and I can plug in negative 2. I can solve for c. So this is our particular solution to this differential equation. So again, this is review. You've done this before. Just the language, adding the word differential equation in there, sort of like, ooh, is this something completely new? No, unfortunately, not like you've seen it before. So that's kind of nice. For what value of k, if any, will this be a solution to this differential equation? So options are to work backwards from the y double prime, which is harder, working backwards is harder, or to take the particular solution and move forward. So we're going to take this particular solution and find its derivative. And then we're going to take that derivative, because our differential equation has y double prime, and find our second derivative. And if this is supposed to be a particular solution to this, this means if we plug in y double prime, this value for y double prime, it should make it true. So in these blue brackets, I substituted y double prime. In these green brackets, I substituted in y. It looks a little bit messy at this moment. And we're supposed to find out if there's a k value that makes this actually work. So now you have this huge big equation, and you have to see if there's a k value that makes this work. Well, what could we do? We could put together some like terms. So if I distribute that 25 into those green brackets, I notice how nice this is, that the sign part goes away. I combine my like terms, and I notice the following, that I've got an e to the minus 4k, e to the minus 4x there, and e to the minus 4x there. Does it make sense then that if these are the same, those things in the purple circles have to be the same? And so k would have to be -2 for this to be a solution. So again, checking if they give you an example of something and say, is this a solution? It's going to be easiest to take that solution and find its derivatives, because you're good at finding derivatives. It's easier than finding integrals. Then you can take your answers and plug them into your differential equation to verify if they work or not. In this case, we weren't verifying. We were trying to find the value of k that would make it work. So when we plugged in our y double prime, and our differential equation also had a y, so that we could plug in as well. Then it was a matter of doing algebraic manipulation to see if there was some way that we could solve for k. So there's particular solutions, and then there's general solutions. The general solution is just when you include the c, saying that c could be anything. So we want to verify if this equation is a solution to this. All right. Going to test your memory. So what do we need to do? Well, we need to find the derivative to test this. But in finding the derivative here, do you see what kind of question this is? What kind of differentiation is this? Implicit differentiation. Do you remember your implicit differentiation? Right? How do we do the derivative when we can't get the y by itself? Most of our equations, we get the y by itself and we just do the derivative. But this one has like, oh, a y to the 4 and has a y mixed in. So we do you remember this? We do dy dx, ddx of this side and ddx of this side and see what you get. Well, if I do ddx of the left side, well, the x squared is easy. That's going to be 2x. In this green box, you have a product rule. So we have to practice our product rule. Keep the first one the same. What's the derivative of the second one? And the derivative of a y is just dy dx. Plus keep the second one the same, derivative of the first one. Notice how I put that all in brackets because we have a subtract sign out front. We're subtracting all of that. So when we do that derivative, we have to subtract all of that. Then 3y to the 4. That's a chain rule. Though 4 would come out in front, subtract 1 from the exponent, then the derivative of the inside is dy dx. And the derivative of any constant is 0. I have a dy dx there and a dy dx there. So recall, when solving for dy dx in implicit differentiation, you'll put everything that doesn't have a dy dx on the right-hand side, move it over. So that involves moving over my 2x, moving over my, what it would be a negative 3x squared y, but moving it over becomes a positive 3x squared y. Then you could factor out the dy dx and divide. So if I factored out a dy dx out of these two terms, I'd be left with 12y cubed minus an x cubed. I could divide by that. And that's my differential equation. And this one is super nice because it matches up perfectly with how they have the dy dx in the question. So you don't have to plug it in or anything. It's obvious that it is the right answer. So far today, except for like Mr. Bean's video where the proportional thing was new and how to set that up, but wasn't super hard. Everything we've done so far is just reviewing concepts in the context of having a differential equation. But this implicit differentiation is probably a good thing to review. So this is one we started with. We had this one and we verified a particular solution to this one. But now the question is asking you to find the general solution. So if we're asked to find a general solution, that means our answer is going to have C's and D's. And in fact, technically, if we look back at when we did this question, we already know the answer. And I'm going to show you, I'm going to go back to that and say, how can I use what we noticed when we did this question before? Right? Here's the question we did it before. And we made the observation, you need the 3x cubed, right? You needed the 3x cubed because that's the only way you get 18x after doing two derivatives. But This didn't matter what was in front of the x, because if you do two derivatives, that goes away. This doesn't matter what you do to have there, because if you do the derivative, it's going to go away. So just thinking of a general solution, I could say, I think it has to have the 3x cubed. But it can have anything in front of the x. So maybe that's my big C. I don't know what letters I chose. We'll find out when we open the box. And it can have any number at the end. That could be my big D. This would be a general solution to this equation, because the C and the D don't matter. You do two derivatives, those things are going to go away. So let's look. I can't remember if I use C1 or C2.
Hi, could I please have office?
Sorry, who?
Lily?
Lily? Yep.
Okay, thank you.
Oh, I use C1. So our first derivative would be a 9x squared plus C1. And then if you did the integral of that, you would get 3x cubed plus C1x, and then plus C2. I sometimes like C and D because those little numbers sometimes get annoying. You could choose either way to do it. But C1 and C2 are any real number. So when you're asked to find the general solution, that's another way of just asking you, find the indefinite integral of e to the x plus 4 sine 2x. So this question is the same as this question. You integrate both sides, the integral of the derivative, that's just going to be y. And when we do the integral of the other side, the general solution would have your plus c. A particular solution means you solve for c. So here, can we plug in 0, plug in 4, solve for c, rewrite the equation with that value of c. So I'm going to let you try the last two there on this page. If you showed no work, you would just write that. If you showed your work, some of that's extra. Probably I would have said, well, you could immediately go to say y equals x cubed plus c, plug in your initial condition, and get c is equal to -2. And the last one, velocity. So working backwards, velocity, integral velocity is our displacement. And we get our plus c, we plug it in, we get our c value. No problem.